only has a magnitude, so what is energy then going to be?
Vector.
Thank you. Who said it? Was it Ken Mark? A scalar.
Same thing.
Okay? Energy is a scalar. It has no direction associated with it. Now in the units, there's a couple ways we can talk about the units here. If we look at the units that we've got here, the units for mass are kilograms. The units for velocity is meters per second, and we're going to square velocity. So the units for this is going to be kilograms meters squared per second squared. That's kind of gross. So what we've done, yeah, we'll get there, Luis. Give me a sec. What we do is we take this unit and we give it its own new base unit. The base unit for energy, Luis has said it a couple times now, was named after a French physicist, last name Joule. So we say that energy is measured in joules, which we give as a capital J. But if we're talking about kinetic energy, talking about kilogram meters per second, meters squared per second squared, that is a joule. Okay? So for example, if I've got a 5 kilogram object moving at 7 meters per second, what's the kinetic energy of that object? Well, I want the kinetic energy. Kinetic energy is just going to be half mv squared. The mass is 5 kilos and it's moving at 7 meters per second. So that's going to be 7 squared. That should be 1 over 2, not 1 over 5. What's the kinetic energy of that object?
Half of 245.
Sorry? Half of 245. That's going to be 122.5 joules. Relatively straightforward, yes? Okay. And what's the hey, don't talk about ice cream. What's going on? Shh, everyone. Okay, forget it. Which is the largest impactor of kinetic energy? Look at the formula, Manuel, and think before you speak. V is not volume. Kinetic energy is half mass times velocity, Connor. There is no volume there. So that cash box is built the way it needs to be built?
Yes.
Okay, so then close it up, and then anything extra you took out of there, I would like you to swap as much of that into bills as you can. Yeah. Okay, so look at what's really important here with kinetic energy, guys. The really big thing with kinetic energy is the velocity. It has the largest effect. Why does it have the largest effect? Because we're squaring it. No, I gotta go back in there anyway. And you're gonna put the money you got here into there anyway. The largest effect is the velocity, which is why we can have really, really small objects. But if you've got a really, really small object moving very, very quickly, the fact that the velocity is small doesn't really matter. If it's moving fast, a small object's still going to mess you up. Which is why even something like a bug, you stick your head or your hand out of a windshield, out of the window while you're driving, it's going to hurt. Or even something small like a BB or a .22 caliber bullet can still really mess you up because it's going very, very quickly coming out of that gun, right? So I say that because I know there are stupid people out in their world, and I know this because I have been one of these stupid people who will do things like put cardboard under your shirt and then shoot each other with BB guns just to see what happens. Yeah, I have been present for an event like this. Really quite a terrible idea.
How'd that go?
It went fine. My cousins were standing far enough apart that we didn't actually do serious damage, but we hurt each other. Okay, so that is kinetic energy. No, let me keep going. Kinetic energy is its own thing. The next classification of energy that we're going to look at is potential energy. Now, potential energy has a whole bunch of different kinds of potential energy. you can have, and I'm just going to list the whole bunch here off the side. Potential energy is energy that is stored in an object. It has the potential to be used later. Chemical is one. What is an example of an object that stores chemical energy?
A glass of liquids that are like, I don't know how.
Okay, Connor, you're really good at making things way more complicated than they need to be. What is Manuel holding in his hand right now? An ice cream cone. An ice cream cone is just a vessel full of calories. That's all it is, Manuel. That's all it is. You're double fisting ice cream cones as we speak. All it is a vessel, a container for turning sugar into energy. So that's ice cream cone is a fantastic source of chemical potential energy. Batteries are another one. Batteries are just chemicals that are waiting to be mixed in some cases, waiting to allow to be to react to produce electrical energy. So you've got chemical energy, chemical potential. You've got electrical potential. Energy that's stored in an object. If I lift my pen, is it moving? No, so it has no kinetic energy. But if I let go of my pen, what's going to happen?
It becomes kinetic.
So kinetic energy is going to get...
There's potential.
Let me speak. Because when I let go, this thing's going to fall, and I'm not throwing it downwards. Like, it's just going to fall by itself, which means there must be the potential stored there for it to eventually turn into usable energy, kinetic energy. So this is the one of the two kinds of types we're going to look at. This is called gravitational potential energy. Can anyone think of another object that we can set up such that when we let it go, it will start moving? An elastic. So an elastic is a fantastic source now not of gravitational potential energy, but what kind of potential energy is stored in an elastic when you pull it back but hold on to it? Yes. Excellent. This is, and the words, yeah, we're going to make sure I use the words properly. Elastic potential energy. Elastic potential energy. These are the two that we're going to focus on in this course. Now, gravitational potential energy is all about having some height. Now, it's due to having some height above some reference point. And the interesting thing with gravitational potential energy is gravitational potential energy is allowed to, it's weird, it can change depending on what you use as your reference point. So for example, that'd be lovely. So for example, me standing right here, do I have any gravitational potential energy?
No.
Who said yes? Why yes, Jasmine?
Because you're standing above the first floor.
So in your case, your reference point is where?
First floor.
The first floor. So if the floor were to give way, or if I were to walk far enough such that there was nowhere anything below me, i.e. like I just walked off the stairs, I would begin to fall. But some of you said no. Those of you who said no, I don't have potential energy, are using what as your reference point?
This floor.
This floor. Okay? And so it doesn't actually matter what your reference point is. And as we do a bunch of these questions, you're going to see that setting your reference point to being a particular level is going to make your life really, really easy or really, really difficult depending on where you choose to set it. So the reference point for gravitational potential energy is completely arbitrary. You get to decide what you call zero.
Do you want me to count it?
Sure.
Do you want me to put it on the bed?
Yeah, that's great.
And I have your Sharpie?
Yeah.
If there are two oppositely magnets that are close to each other, would that be potential energy?
Yes, there is also magnetic potential energy. But we're totally ignoring magnets. Magnets are weird.
I wanted to say charge polarity.
That's electrical. Yeah, electric potential. Yeah. Which we're also not talking about this year. Now, if you can fall, you have gravitational potential energy. But as you guys have already said, is it possible for me to fall right now from this floor to the first floor?
No.
Why not? Maybe, right? Theoretically, yes, but some of you would say practically no. So again, there's a reference there. The expression for gravitational potential energy is going to take into account how high you are above something and the force that is going to act on you should you leave that height. What force is going to act on us should we leave this height? Gravity. And the expression for the gravitational force is mg. So therefore, potential energy is going to be given to us as mgh. Those three values multiplied together. Where m is mass, I should be in green, oh, whatever, that's fine. M is mass, just in case any of us get confused, Connor. G is, little g is acceleration due to gravity. And h is the height above whatever you call your reference point. The units, let's take a look at those again. I'll keep these units up here so you can see how this works. Mass is in kilograms. The acceleration due to gravity, what are the units there? Not meters per second. Meters per second squared. And height is measured in meters. Oh, look. Meters times meters is meters. So we actually have the same formulation, even though we're talking about a different kind of energy. We have the same formulation, kilogram meters per second squared. The same thing we got up here for kinetic energy, we are also going to call this thing a joule because it is it's a form of energy. So, for example, a 10 kilogram object at rest at a height of 12 meters, what is the potential energy in that object? Well, potential energy is going to equal mgh. So our mass we know is 10. Little g is 9.8 because we're going to assume we're at or near the surface of Earth unless otherwise specified. And our height, we're told, is going to be 12. It's not giving us an option to choose a reference point. Manuel, what's the value? Which is going to be 1,176 joules. That's it. Nice and easy. Comments, questions, concerns on anything here so far? I know we're distracted by ice cream and money being counted and all that jazz. Okay, flip the page. There's another kind of potential energy we're going to talk about right now. Sorry? 1,176 joules. Yes, Luis. No, it's just a definition. It's just defined that way. Okay, so, hey, not bad. More than we spent. That's good. We have profit. Okay, so let's carry on here. The second kind, we already talked about it. I already told you we were going to talk about it, is elastic potential energy. And this is due to, oh man, I'm working off of nothing here. Energy stored in an elastic material there's a whole bunch of different kinds of elastic material. Like a rubber band would be an elastic material. Like a car tire, the rubber there is an elastic material. A spring, a slinky is an elastic material. So elastic potential energy is due to energy stored in an elastic material caused by either a stretch or compression, depending on the material. So this one, notice, and I didn't address it with the gravitational potential energy, but potential energy is for whatever reason, don't ask me why, I don't know, the capital letter U is used for all types of potential energy. So sometimes it's also given to us as PE with a little lowercase or a subscript s for spring. So sometimes this is also given to us as U sub s, whatever. I will use PES, potential energy spring. And the formulation for this is 1/2 kx squared. And I've got to look up one thing here, because I definitely forgot to write it down. If we take a look at the units here, and this is what I just had to look up because I couldn't remember it, but does anyone remember the units for K? I shouldn't have looked that up. I should know what K is.
K is the constant, so there is no.
No. Coefficient of friction has no units. K has units. It's newtons per meter. It's newtons per meter. So if we look at this, this is going to be the newtons per meter times meters squared. But if we look at where the newtons come from, newtons is force. Force is mass times an acceleration. So this is actually going to be our mass times our acceleration divided by a mass. Sorry, divided by, no. Mass times meters per second squared divided by meters times meters squared. Look at how this cancels. We're still going to get kilogram meters squared per second squared, and that's still going to be equal to our joule. We want things to remain consistent, and friggin' A, look at that, they do. Okay? So, for example, what is the potential energy in a spring with a spring constant of 4,680 newtons per meter that has been expanded by 15 centimeters? This is a real life scenario. This is a very large spring constant. And if none of you have ever built a trampoline, I feel sorry for you. This is something that I miserably had to do every spring growing up because we had a trampoline and my dad and I would rebuild it so it wasn't sitting outside all winter. This is the spring constant for a single trampoline spring. And this is the rough extension that we had to do to hook it up to the mat and then pull it to the bars that would go around it. So the potential energy in that spring is going to be given to us like this. PE spring is going to be equal to 1/2 kx squared. We can shove some values in here. This is going to be 1/2 times 4,680 times now 15 centimeters. What do I have to do with that? To convert that thing into meters, 15 centimeters is? Thank you, 0.15 meters. So that's going to go in here. So it's going to be 1/2 times 4,680 times, what was that, 15 squared is 225, so it's 2.25 times 2,340. I can't do that in my head. Someone with a calculator, what is this? Oh, don't worry about the black box. Don't count the black box.
No, I'm not counting.
Oh.
I'm just
Or is it?
memorizing it.
Is what, sorry, James? 52.65. That seems really small, but then I guess there's no way it's 52.65. Is it really that small? 0.5 times 4,680 times 0.15 squared. Wow, that's waste. I'm sorry I didn't trust you. That's really weird. 52.65 joules. Okay, so that's elastic potential energy. What I'm doing here is I'm just gonna introduce a whole bunch of these things, and then when we're done, release you to work on a bunch of them. So, we've got kinetic energy, we've got gravitational potential, and we've got elastic potential energy. The next thing we're going to deal with here is this idea of work. Now, okay, you need to close that box. Okay, thank you. That's okay. Work. The definition of work, there's a few definitions we're going to give you. The first one is this. Work is done if a force is able to or is acting over a distance. That is the physics definition of doing work. Now, if I asked you to hold up something heavy, would you feel like you are working?
I understand.
Answer my question, Connor. If I handed you something, Connor, I hand you something heavy, I say, here, hold on to this for me.
Initially, it's light, but over time,
You're going
it
to
gets
feel
harder.
like you're doing work.
I understand.
But are you doing any work?
No.
No, from the physics definition, unless you take that object and move it somewhere, you are not doing any work. By the definition laid down by physics. Those two are yes. Sure, I have no idea where he is, but if you want to try and find him, you're welcome to do it.
What do you want to do with this?
That's mine?
Yes.
I want to, what was the number on that again? Oh yeah, right. Throw it in the, there's there's 4 cash boxes in there. The heaviest one in there. Yeah.
Oh, what a cat.
Okay, so work is defined as a force acting over a distance. This is our first definition for work, guys. Jasmine and crew. Hey, let's get buddy guy out of here. Go away. Go away. Okay, he's probably still there. Work is a force times a distance. So what are the units of work?
Joules.
It's going to be force is newtons times. But look at this really interesting result. Newtons is, we've already established, kilogram meter per second squared multiplied by meters is going to give us kilogram meters squared per second squared, which means that work is also measured in joules, which means that work is actually a type of what? Work is going to be related to energy somehow. We're going to define how that is in a second here. So, using our first definition here, using this definition, thanks Riley. A student pushes a box with a force of 80 newtons along a surface that is 3.5 meters long. How much work does the student do? Oh.
Work is everything that produces energy.
We're getting there, not necessarily. Work is a force times a distance. So the force was 80 newtons. The distance was 3.5 meters. Cool. So, and it's important, right? Who is doing the work here? I meant to, it's 280, yes. That means I made a mistake back here. Oh, yeah, that's why I made a mistake. 280 joules. So, another example, if the force of friction acting against the box, so we're going back to this same example, there's a box here, that should be 80, no, I'll leave it 8. We'll say the force of friction is, you know what, no, I don't want that, I want 80. I want one of these to be consistent. So if the force of friction acting against the box is also 80 newtons, how much work is done by friction? Well, work is equal to a force, 80 newtons. There is a distance because it's the same, it's attached to the same example back here. While the student was pushing the box with 80 newtons, friction was acting at 80 newtons against that motion. Sorry? So let's look at okay, Jasmine and Connor, one sec. Let's look at what's happening here. The work, if I'm pushing a heavy object, 80 newtons that way,
Friction's resistant.
okay, my work is done in that direction. but work doesn't have a direction. So how we talk about this is we talk about putting work into the system. I have done work on the system by pushing it this way. If, as I'm pushing this way, friction is pushing back against me, friction is doing, you can think about friction doing work which way?
Opposite
The other way.
direction you're opposed.
But work is a scalar. So how does that pop out? Well, we would say then that because friction is acting against the direction of motion, it's going to show up here as having a negative displacement because you're pushing against the direction that friction is acting. So 80 times negative 3.5, that's going to equal negative 280. But in this case, because work is a type of energy and energy is a scalar, what does it mean for negative work to be done here?
It means that you're balanced, you're forcing your balance.
Well, it means that as I'm putting work into the box, friction is pulling work out of the box. And in the form of what is friction pulling energy out of the box? So I'm pushing, causing the box to move. Friction is acting with negative, so if positive energy means it's going into the system, negative energy means it's coming out of the system. How do we know that friction is pulling energy away? What is generated? Heat. Primarily, sound a little bit. Sound is much smaller than the heat that's getting pulled out of here. Okay? So this is coming out as heat. You found them?
Yeah, he's a teacher.
Cool, thank you.
Where most of the teachers are.
So what then is the overall work done on the box? Well, work net is going to be equal to we're going to think of it two ways. Either it's the, like we had before, it's the sum of all the work. Or you can think of it as F net times the distance this thing acts. What is, if we sum up the work, it's just going to be the 280 joules minus the 280 joules. It's going to be 0. The net work done on the box is 0. Because everything I put in, friction took away. Or you can think of it like this. I am pushing to the left with 80. Friction's pushing to the right with 80. So what's my net force here? My net force is 0. Times the distance we were acting. So it doesn't really matter which way you approach this. You can sum up all the works, or you can use this idea of, well, work net is going to be F net times our distance. Either way, it's going to give us the fact that as far as the system is concerned, no work was done because friction took away everything we gave to the box. So when it says down here, I actually short-circuited myself here a little bit. What is another way to find net work? I did both of them right here. This is what I mean. Either it's the sum of all the work, or it's work net equals F net times distance. These are the two ways you can do it. Comments, questions, concerns so far? Okay. Flip the page. Work is, because it's also measured in joules, it is also defined this way. Not just as a force times a distance, but also as a change in energy of an object. So the expression for that then is work is equal to delta E. We remember delta from way back, means a change in. So this is going to be equal to your energy final minus your energy initial. So if a 5 kilogram object is accelerated from 2 meters per second to 5 meters per second, and it asks us to find the work done, we don't know what the acceleration is, so we can't find the force acting on this object, right? Like, we could use work equals a force times a distance, but I don't know what the distance is, and I don't really know how long this took. I don't know what the acceleration here is. Instead, what we can use is this formulation for work where we say, okay, well, work is a change in energy. What kind of energy does my object have? That's not a kind of energy. Kinetic energy. So to find my work, I'm going to use energy final. Well, the kind of energy it has is kinetic. So we're going to have kinetic energy at the end minus the kinetic energy it started with. To change the kinetic energy of something, you have to do work on it. So my kinetic energy final, that's just going to be half mv final squared minus 1/2 mv initial squared. So at the end of this thing, how much kinetic energy does our object have? Well, 1/2. The mass of my object was 5. How fast is the object moving at the end? 5 meters per second. So I'm just going to plug that value in here for my final velocity. Minus 1/2 my mass times my initial velocity squared. What was my initial velocity? 2 squared. How much work was done while we accelerated the subject? Someone help me out here.
I'm coming.
Hey, none of that. None of that. How much energy? 52? 0.5 joules. Another example. We're lifting a 10 kilogram box 5 meters straight up. You could use a crane, maybe you're climbing a ladder, I don't know. 10 kilogram box is being lifted 5 meters straight up. What was the work done to do that? Well, we're still going to use this idea of work is equal to a change in energy. But in this case, what kind of energy does our object have? It's going to have potential energy. We don't know. We don't care what happens in the middle. Yes, the object had to start moving, but it's going to stop moving as like when you get it to the top, right? So we don't care about what happens in the middle, the kinetic energy as it moves. All we care about is the fact that at the end of this thing, there's going to be potential energy now. Minus whatever potential energy I had to start with. Now, assuming our potential, so actually I'll put this in here, mgh final is going to be our expression for potential energy, minus mgh initial. The final and initial are changed to the height because the mass of our object isn't changing. We're going to have our 10 times 9.8 times 5. By putting 5 here, what am I assuming my initial height is? Think about what you're saying before you say it. If I'm putting my 5 here as my final height, then what is my initial? What am I assuming my initial height to be? 0. Thank you. So then this then is going to be minus 10 times 9.8 0.8 times 0. So then my final potential energy is going to be 490 joules as we raise our object up. We've given it potential energy. Now, if we let it go, all of this potential energy is going to get turned into what? Good, kinetic energy. So as it hits the ground, it's going to hit the ground with this much kinetic energy because that's the energy that was available to it. That make sense? Yeah. That's as far as we're going to take it today. We're going to stop right here. I want you to do a little bit of practice this weekend. Here's the practice I want you to do. Okay.
1 to 10?
No, not quite. Hold on. I want you to do. Actually, yes. I want you to do 1 to 10 on this page. This is Friday's homework. And then I want you to flip the page. And I want you to do 1 to 5. Okay. We'll look at the rest of this on Monday. Bell, I don't know why the bell hasn't gone. Isn't it supposed to go 1:15?
1:20, I think.
Oh, 1:19. You have 4 minutes. Do start working on this then. Do not pack up. There you go. Welcome to Work and Energy. Play with this stuff. 1 to 10 and 1 to 5. Go.